Okay, so today instead of doing the finite state methods for the morphology, I will talk about something else. I am just changing the timeline of the course schedule a little bit. I will talk about the word meanings, and how we represent the meanings. So it will be way up. Remember our hierarchy of processing the words and the sentences. We said that we will start with the morphology and then the syntax and the meaning and etc. We are kind of doing it before the others because I am going to give you a homework about the minimum edit distance, and this minimum edit distance will be about matching two different texts, and if the words are different then their meaning should be similar. That's why you need to know about this. So I'm going to talk about the meaning of words first. Okay, so that's the definition of meaning from the Webster dictionary. These slides, I don't know where I got them, but I am going to put the slides to the our Teams page. I am going to follow these slides, and mostly these are the slides from the Manning's course. Manning is one of the authors of the our book, NLP book. Okay, so these are some of the meanings of the word meaning from the Webster dictionary. It's an idea that is represented by a word or phrase, an idea that a person wants to express by using words, etc. The idea that is expressed in a verb or writing, and etc. So meaning has many different meanings, the meaning of the meaning. And in computational linguistics, NLP, we are going to well, I mean, we are scientists, we are engineers, right? We have to work with numbers, so we are going to assign numbers to words that will represent meanings. Okay, so one way of doing this is, okay, if I, let's say, take the Turkish dictionary. Usually the Turkish dictionary starts with ab, aba. I guess ab means su, aba means aba. Everybody knows it, and it goes like, the last word would be usually what, zürafa? What is the last word that you can think of? Yeah, maybe zürafa, etc. So I can give a single identifier for each word. Word number 1, word number 2, word number 40,000. That would not be a very good idea to represent the meanings, right? Because if I'm assigning this kind of stuff, this kind of number to for each word, okay, dictionary order doesn't have to represent the meanings at all. It's the dictionary order. So when you say, let's assign close by numbers to words that are similar to each other, for example, maybe ab, which means su and su, should have similar numbers. If this is 13,000, this one maybe su is 13,722. Okay, and you might say that, okay, this is good, but su has many other similar words to it, syntactically and semantically. For example, in Turkish we use su and ekmek very close by, right? Should I keep ekmek is in between them, and etc. So it becomes a very difficult problem to assign such numbers, especially a single number, to each word to represent meaning. Okay, with these kind of problems, engineers usually say that, okay, let's use a different space. I mean, we don't have to use a one-dimensional numbers. Let's use more than one-dimensional space, two-dimensional, three-dimensional, and dimensional space, and that way we can express these kind of similarities in terms of syntax and semantics and co-occurrence and etc. That's what we are going to do. That's what we do with engineering, right? I mean, when you need to represent something, okay, For example, if you like to represent numbers, double numbers like this, these are nice, but how about this? If I like to represent a number like this, I cannot represent it, okay, because I don't have a corresponding one-dimensional number for this number, square root of minus 1. So let's go to two-dimensional world, okay? If I represent each number with part A and part B, okay, all the numbers that I know are, all the double numbers will be in part A, but if I need to represent something related to the square root of minus 1, then I am going to make this non-zero and etc. Then you have invented complex numbers, right? I mean, if something doesn't fit in a single dimensional world, let's try the two-dimensional world. And if you're in the two-dimensional world, now I can express many things that are useful. I can solve many equations using the complex numbers and etc. This is something that we do all the time, and we are going to do the same thing with the representation of the words. We are going to assign, okay, we are going to assign these kind of vectors for each word, okay, and these words will represent these vectors will represent the words like this one, banking, and we are going to satisfy we are going to satisfy we are going to satisfy each of those requirements, like for example, banking and bank will have similar vectors, okay. What else? Banking and money will have similar vectors, etc. These will be called word embeddings. We are gonna embed our words in an embedding space, which would be, in this case, I think it's 10 dimensional, but we are going to use maybe 100 or 200 dimensional words, okay. And for some reasons that I'm going to explain in a few minutes, we are going to call also they are distributed representations, and they will be very useful. They will be very useful, and from that point on, instead of using words, we are going to use these vectors to represent words, okay. If somebody gives me a complete sentence, for example, I like online banking, okay. I like online banking, okay. This sentence will be a 200 dimensional vector here, another 200 dimensional vector here, 200 dimensional and 200 dimensional. So it's going to be a sequence of 200 dimensional vectors that will represent our sentence. If you combine all those vectors together, okay, if you combine them, take the average, take the mean or whatever, that's going to represent your sentence. So that way, now I can use all the mathematical techniques that I used to use for the numbers for the words. The important thing is that where these vectors come from, okay. How am I gonna assign these vectors for each of those words? That's what this lecture is about. Let's assign vectors to words so that this kind of stuff is more meaningful. So those vectors will capture both syntax and the semantics properties of the words, okay. Let's go back to the beginning and let's talk about it, okay. Some would say that, okay, to represent the meaning, we would use resources like WordNet, okay. WordNet is a human constructed network of words. Some very smart people, they sit together, okay, they define lots of relationships between the words. For example, they define this hierarchy of the words. For example, the is a relationship. Give me lots of is a relationships between panda and some other words, okay. Panda, you know object-oriented programming, right? In object-oriented programming, there is an is a relationship between two classes. if you drive or extend one class from the other one. For example, the typical one is a person, I have a person class, right? I drive a worker class from a person class. Each worker, there is a relationship between them, okay? Each worker is a person, but worker is a specialized person. Why? Because worker has other properties than a person. Person has a date of birth, person has a TC kimlik numarası, person has a name, as an etc. an address. On top of it, worker has all of them. On top of it, worker has maybe monthly pay. How much does this worker win? How much does this worker paid every month? How much tax this worker pays to the government? And what is the starting time for the work, and etc. So it's a specialized person. So there is a relationship between them. It's called hypernyms. If you have these kind of relationships between two words, it's called hypernyms. And some people sit together and they mark all the hypernyms for all the words. We say that a panda is a prasinid, I don't know how to read it, carnivore, then placenta, then mammal, okay? So it is going larger and larger. Vertebra, etc. It goes animal, then it's an object at the top. Everything is an entity. All the words are entities in this world. So you get this, this is a real word that, okay, it is a Python piece of code, okay? So I imported worded as WN, and I got the synset panda, that means, okay, synset sanda from this one, and I asked this hypernyms of lambda, and it will give me this. I don't have to get the hypernyms. I get the synonyms, okay? The same meaning words. Here, for the good, goodness is the same meaning. Commodity, remember we can use good for mallar, mal içinde kullanıyoruz yani good. Okay, commodity. Sometimes I use good for the, okay, I use good for the as a noun. I use good for as adjective, okay? Adjective meaning of good is good. Sometimes I use good as like full. I am good. I am okay. Karnım tok gibi. Sometimes it is good. These are types of adjectives. They are not. I'm not going to talk about them. Okay. Honorable, respectable, beneficial, right? Just, upright. Sometimes I use as a adverb, good. Okay, or truly, I did it good, and I read it good, etc. So if you have such data sets, then like WordNet, then you are fine. But the thing is that you need lots of manpower to form such data sets, WordNet, and they are specific for English. It is very manually tiring process, very expensive process. It is open the errors and etc. There are many problems like okay. We continually add new words to language, okay? And these are some of the words that are added with a different meanings to English in 2010s, okay? So whenever you add a new word, you need to update all of your WordNet data set, and sometimes words stay the same, but meaning changes, okay? For example, ninja has a very different meaning like 20 years ago. Nowadays, you use ninja to represent somebody that is very good at something, right? Say ninja of the Python language means that guy is very good at Python, right? So it is impossible to keep up to date, etc. It is subjective, requires human labor, and actually, I mean, it gives you all kind of information about the similarities. It kind of all kinds of information about the similarities or the is a relationships or the opposite meanings of it, you cannot get numbers out of it. I mean, how similar is good to full and let's say just? How similar are they? Well, saying that they are similar is not a good thing. I need a number between 0 and 1. 1 means they are very similar, 0 means they are not similar at all. So this doesn't give me that kind of a measure either. So we are going to do some representation of the words. So if I represent two words by a vector, okay, what is a vector? Okay, in our two-dimensional world, this one is a vector, okay, this one is another vector, okay. How similar are these two vectors? There are many things that you can do to measure the similarity, okay. One of them is this. We like to measure this angle, okay. The similarity between these two vectors is the angle between them, okay. So that means what? This red vector and this blue vector are very similar because the angle between them is 0. The angle between them is 0. Okay, we like this angle measurement because mathematically we have a very compact representation for it. You know the dot product between two vectors. Okay, I have this vector A, B, C. Let me write it in the vector form. Okay, A, B, C is a vector, and I have this vector D, F, E. The dot product between two is just simple A times D plus B times F plus C times E. That's it. Okay, that's the dot product. That's the dot product. The nice thing about this dot product is if these two vectors are orthogonal to each other, okay, there is a 90-degree angle between them, this dot product will turn out to be 0. It will be just 0, okay. Smaller the angle between them, okay, larger the dot product. So that's very nice. That means what? If I assign vectors, if I assign a single vector for each word in my dictionary, then to measure the similarity between two words, all I want to do is just take the dot product between these two vectors. Okay, take the dot product between these two vectors. Okay, that's what we are going to do. But before we start, people try this kind of representation techniques. This is still being used. It is useful for many numerical methods. One-hot vectors, simplest vector approach that you can use for representation of the words. It says this: if I have, let's say, 500,000 words in my dictionary, to represent each word, I will have a 500,000 dimensional vector. It's a binary vector, okay? Its size is 500,000, it's very large. Only one of the elements is 1, the rest of them is 0, okay? To represent a motel, you make this 1. To represent a hotel, 2 words, you make this 1. So it is as simple as this. So if I take the dot product between these two, what would I get? What is the dot product produced between hotel and motel? 0, right? Because they are orthogonal to each other. They are orthogonal, right? Because in this 500,000 dimensional world, okay, there are 500,000 different orthogonal vectors, and this motel and hotel, they are orthogonal to each other. It is 0. That means what? They are not similar to each other. And to make, if two words are similar to each other in this representation, they have to be the same word, right? Otherwise, they wouldn't be similar to each other. So it's a representation method, but it's not a very nice one because it is very limited in terms of finding the similarities. But still, we are going to use this kind of a representation as a starting point. for as a starting point to get to what we want actually. Okay, so this one is bad, or the vectors are orthogonal to each other. Okay, there is no natural notion of similarity for one-hot vectors. Instead, we will learn to encode similarity in vectors themselves. Starting from 1950s, people know this idea. Okay, this guy, okay, he said that you know this saying, right? You should know a person from the friends that he or she keeps. Okay, he says the same thing. You shall know a word by the company it keeps. Okay, so what does that mean? To represent a vector, to represent a word by a vector, you should look at its neighboring words wherever it passes. Bank has many meanings. I think we talked about this in English. Okay, this is banking crisis. So this is talking about the banking industry, I guess. This is banking regulation. Again, it is talking about the banking industry again. The third one is talking about the banking industry again. So as you see with this word of banking, these kind of words happens a lot. Crisis, government, Europe, regulation, hedge, pudge, I don't know what it is. Okay, system, banking system. As you see, by paying attention to these kind of words, okay, by paying attention to these kind of words, you are getting lots of idea about this word banking. So yeah, all I am saying here is that whatever vectors we are choosing for this word, those vectors should be similar to the vectors of these words. Okay, so because they are happening together, so they are keeping each other company, they are friends with each other, so their vectors should be maybe the same. Okay, maybe you guessed it, we are going to find a unsupervised system that will assign these kind of vectors to these kind of words. Okay, we are going to assign those vectors in a way that the similarity between these words will be high, or the multiplication of the vectors of this word and this word will be high. You might say that, well, there are lots of words in these sentences like to, in, the, it's, just, has. Well, these kind of words are going to be very similar to every word, okay, but they will be similar to, for example, the word the will be very similar to this or that or a, because if I take this the out, okay, replace it with an ea, just a letter a, okay, the sentence can be a meaningful sentence too. So both of them should be okay. A and the should be happening can be happening in the same position. So they will be assigned very similar vectors, and we are going to see how it happens. Okay, so we already talked about it. And the reason why we call these kind of vectors distributed representations, okay, this is a distribution, okay, distribution of how many times banking and government happening together, distribution of how many times Europe and banking happening together. Okay, so this distribution will give us the context. Okay, so these are the main motivations for our distributions. And let's say if I somehow I achieved this picture, somehow I represented my words in two dimensions. I am not saying two dimensions are enough, but I say I represented them in two dimensions, and this is x, y dimension, and this is the x dimension, okay? And if I put the words at their respective positions in this two-dimensional world, you see be, are, is, being, been, okay? They are all very were, was, okay? They are all very close to each other. Their vectors are very close to each other. And if I draw like this is a vector, another vector, another vector, another vector. As you see, the angle between them are very, very small. Likewise, this say, think, expect, see, meet, give. These are all kind of words, right? These words come together. So say and think, okay. Say and think are close in terms of their meaning, right? Say and think in terms of their meaning. Also, they are close in terms of their syntactic position, right? They are both verbs. Come and go, they are almost okay together. Okay, although they are opposite to each other, they are so related to each other, right? They are similar. Okay, they are similar. The reason why come and go is happening together is instead of using come, if I use go, my sentence is still valid an English sentence. So instead of come, I can go, I can use go, etc. Okay, so this is what's going to happen, and we are going to do this a lot. As I said before, I don't think that we are going to represent a word by just two-dimensional vectors. We are going to represent them 100-dimensional or 200-dimensional vectors. But I'm going to show you one way of reducing that 200-dimensional vector a single two-dimensional vector. Okay, just the purpose of the visualization, and we are going to see that we can achieve this. Okay, so to produce these vectors, I am going to look at this word-to-vec approach. Word-to-vec. We are going to convert words to vectors. That's why it's called word-to-vec. Niccolo and the others, they proposed this approach in 2013. Well, before them, of course, the representing words with vectors were very popular, but they came up with an approach fully unsupervised. All you do is, for example, how many words are there in Turkish Wikipedia? If you take the Turkish Wikipedia, there are more than 1 billion words in it, right? You give Turkish Wikipedia to this word2vec program, like 400-500 lines of C code actually, this one, not much. And it runs on it for 2-3 hours on a good machine. And it comes back and it says that for every word that I have seen, I am assigning these 200 or 300 dimensional vectors. Okay, and it works very nicely. Okay, so how it works is this: at the beginning, it assigns a random vector for each word. Okay, it assigns a random vector for each word at the beginning, and then let's say if I have 1 trillion words happening in Turkish Wikipedia, how many unique words are there? If I have what is 1 trillion? This is thousand, million, billion, and trillion. Okay, let me put these, okay. If I have 1 trillion words in Turkish Wikipedia, how many unique words are there? Well, Turkish dictionary has maybe 40,000 words, but as you know, in Turkish Wikipedia, we don't have only the root forms of the words. We have lots of morphological modifications to it. I don't have just a single kitap in that Turkish Wikipedia. I have kitapları, kitaplarının kitaplarından, etc. So usually we have 1 million unique words, around 1 million. So it's going to produce 1 million 200 dimensional vectors. Okay, so that means what? I will have a vector for kitap, another vector for kitaplar, Okay, the vectors for these two words are very, very similar. So if I do the dot product between them, I will get a large number. I know this, but nevertheless, their vectors will be different. Their vectors will be different. Okay. Kitap okudum, kitaplar okudum. Okay, they can happen, right? So I can put one vector instead of the other one. So I expect this to happen. Okay, good. So let's see how this word to vec works. Later we are going to look at it more in a more careful way. So basically it works this way. It says that, should I do that? No, maybe I should. I'm going to erase it everything. I will end up writing the same thing, but okay. So this is what we are saying. Let's talk about probabilities, and I will make a connection to the vectors later. Let's say given that this is our window of size 5. I took English Wikipedia, okay. I took all the sentences, and I am looking at this. I am looking at this window of 5 words, okay. I say that I have a center word, so this is the center word C. These are the context words O, O, O. Okay, these are the others. Or should I say, not the center word, but the context. Anyway, I mean, doesn't matter what I use. Maybe I can change it later to C's, the O's, whatever. Okay, so this probability says that given WT is this one into, what is the probability that I will observe this word banking? Can you calculate it? Okay, conditional probability. Okay, given WT, what is the probability of WT plus 1? So this is typical straightforward prior probability calculation stuff. If you remember from your high school years or the middle school years, whatever, to calculate P probability of A given B, okay, probability of A given B, usually this B is given, right? If I multiply this with probability of B, I would get what? I would get P, you tell me what? P, A and B happening together, right? That's the definition of conditional probability. That's the definition of conditional probability, or I can write it this way. A given B is equal to A and B happening together, probability, and probability of B. Okay. How do you calculate the probability of B? Let's say probability of into. What is the? I am just picking one random word from English Wikipedia. What is the probability that I have seen word into at that position? How do you calculate that one? Give me a one way of. There are many ways of calculating it, but our expected probability would be what? Maximum likelihood stuff. Somebody gave me the English Wikipedia, the whole Wikipedia. Let's say there are 100 trillion words in it. It is much larger than Turkish Wikipedia, right? Let's say 100 trillion words in it. I just pick a word from that out of 100 trillion words, and I'm asking what is the probability that this word is into. How do you calculate it? Count of into over 100 trillion words. So it's a very small probability, but it's a probability, right? You can calculate. So I know how to calculate PB, right? How about this one? What is the probability of into banking? So out of all the word pairs that is happening in English Wikipedia, how many of them are into banking? So the count of into banking over count of all the word doubles. So that's going to be a very small number. You divide this by this one and you calculate this one. Okay? You calculate this one. What I'm saying here is that however you are calculating it, okay, however you are calculating it, I just gave you one way of doing it. One way of calculating this probability using maximum likelihood estimation, okay, but probability doesn't have to be calculated this way. Probability doesn't have to be calculated that way. Probability is the definition of probability in artificial intelligence is this: what is my belief in this number? Okay, what is my belief in this number? And I calculated my belief this way using maximum likelihood estimation, but it doesn't have to be calculated that way. I'm going to calculate some other way so that our vectors assigned for each word would be meaningful. That's what we are going to do. So I am saying that define this probability in a way that, okay, this probability is high, this probability is high, this is high, and this is high. It's kind of saying that if I know that WT happened, banking happening in the same window, the probability of banking happening in the same window is high. Crisis is high, turning is high, and problems is high. Okay? So that's the meaning of it. This is the center word at position T, and all of them are rest are the context words. That's what we're going to do. Let's assign vectors to each of these words and use those assigned vectors in this probability calculation so that this probability turns out to be high. Okay, that's what we are going to do, and for that one, okay, very large equation here. It says that get the Turkish Wikipedia, the whole words from 1 to T. T is the number of words happening in Turkish or English Wikipedia. So we are talking about 1 trillion here. For each of those 1 trillion words, calculate these probabilities. Okay, and multiplication of these probabilities should be as large as possible. Okay, we are going to calculate. Well, of course, it looks like it's a very large multiplication. Definitely, we are going to do the floating point underflow, because remember, P is a probability. It has to be between 0 and 1. If you multiply 1 trillion times 5 numbers, if m is 5, okay, it's going to be a very small number, close to 0, and we are going to underflow. That's not going to be good, but let's forget about our numerical problems. We will concentrate on other stuff. Okay, we say that whatever you are doing with these, okay, vectors of the words, let's say our vectors are stored into this theta, is a set of, let's say, vectors. Okay, find me such vectors so that this probability multiplication makes maximum. Or usually in the numerical methods world, we like to minimize stuff, and instead of multiplying, we like to add. So if I take the logarithm of this equation, I would okay, end up adding all those numbers, because you remember with the logarithm multiplications becomes additions, and we take the logarithm and we take the minus, so that instead of maximizing this, we are going to minimize it. This is our objective function. Minimize this summation, this large summation, by playing with these vectors. Okay, we are going to minimize this summation by playing with these vectors, but still I didn't tell you the meaning of the P is? How am I going to calculate P? Okay, given those vectors. And the thing is that it's not that difficult actually. Okay, this is how I am going to calculate P. Given the C word, okay, the context word, what is the, okay, this is using exactly just the opposite of what I told you. C means context word, not sentence. Context, other words. The center word is this one. What is the probability of O? Okay, so this is how am I going to do. Each word has a okay vector. Okay, vector of C and vector of O. I am going to dot product them. Okay, I'm going to multiply them, and I expect this dot product to be larger for similar word. But okay, tell me this one again. I have two vectors A and B. I am taking the dot product. What is the result? Is the result a scalar or a vector? It's a scalar, right? So what is the limit for that scalar? I mean, what is the smallest that scalar can be and largest that it can be?
Minus infinity plus infinity.
Yeah, from minus infinity to plus infinity, right? Because I am taking the dot product of two things. So, well, what did I say? I said that if these two vectors are similar to each other, the multiplication will be large. If these two vectors are orthogonal to each other, they are zero, right? The dot product will be zero. If they are opposite to each other like this, right? It will be some negative number, large negative number. Okay, so we have a problem here. To calculate the probabilities, we have to do something. Let's look at this function. Any function that takes the exponentials will be like this, okay? E to the x, okay? E to the x. E is something like 2771 something something. That number to the x will give me this, okay? Exponential. And what is this point? E to the 0 is what?
1.
This is 1, okay? And this will never become 0, doesn't matter, okay? Where you go at the negative infinity. At the positive infinity, it's going to be very, very large, okay? At the negative infinity, it's going to be very, very close to 0, but it's not going to be very close to, it's not going to be 0. I know this one. The nice thing is, whatever you put here as an x, okay, this function will make it a positive number, right? It's going to make it a positive number. So it makes sense to do this multiplication, okay? Multiply two vectors, okay? Multiply two vectors and take the exponentiation of it so that the upper part is definitely a plus, a positive, a non-negative number. It's definitely a positive number. It cannot be a 0. It cannot be a 0. And let's look at this bottom part. What does the bottom part say? It says that, what is this? Can anybody tell me what this is?
All words?
W, yeah, is an element of V. What is V? V is all the words in my Wikipedia dump, okay? All the unique words. How many unique words did I have? 1 million, right? 1 million. Try the similarity between this word, okay, okay, that word, center word, with all the words, okay. This is only about context word and the center word. This is about the C word and all the other words in my dictionary, or not dictionary, sorry, in my unique Wikipedia words, right? So you expect this to be between 0 and 1, right? It cannot be 1, it cannot be 0. Why? Because none of them will be 0. There is definitely a value here. It cannot be 1. Why? Because there is no multiplication as large as this summation, so it's going to be between 0 and 1. Okay, surprise for you, I found a probability representation of such a question. You give me a word, given that word, what is the probability that this context word is happening around that word? I can calculate it this way. This is the model. I can write my probability rules the way I want, as long as I am obeying the rules. What are the rules? Probability should be between 0 and 1, right? It should be between 0 and 1, and that's the basic rule actually, and that's it. I am calculating my probabilities this way. Okay, so if this is my probability calculation, this theta is the assignment of all those vectors for each word, then I can calculate this objective function. Remember, this objective function needs to be as small as possible. How small, I don't know, as small as possible. Okay, so how am I gonna do this? This is what I am going to do. This is what I am going to do. Okay, I will take windows like this. Okay, I will put, this is the word in the center, these are my context words. Okay, I will calculate each of these one by one. Okay, and add them together, and then I will move to the next word, and this one becomes the center word, and all the other ones are the outside context word. So my notation is this: this is the center word, these are the outside context word. So C means center, O means outside. Okay, so I'm going to add them up and add them up. At the end, I will get a number. I will get a number for this one, and I like that number to be small. So what am I going to do? I said that at the beginning I assigned random numbers to the vectors. I am going to change my vectors a little bit, and I will test it again. I'm going to see which one is smaller, this one. So I said that whatever I did was right, so I am going to use this representation instead of the other one. Okay, so that's what I am going to do with the word to vec. Start from a random word assignment, word vector assignment for all the words in my corpora, for all the words in my dictionary, then calculate this one on my data set and get the number, and then do the modification on my vectors again, do this calculation. Whichever gives me a smaller result, better result, I will keep those vectors and continue this until I don't get any improvement. Of course, the way I told you is something like, well, would this work? I mean, just random movements and etc. Well, we are going to do better than some random movements. We are going to do better than that, and it's going to work beautifully. Okay, but we will never claim that these are the best. We will never claim that these are the best word vectors that can happen. And we won't be surprised if somebody else finds a smaller number of j theta, okay, and that will be accepted. What did I say last week, or the week before that week? We said that we are trying to find good enough solutions. Okay, it's an artificial intelligence problem. There is no perfect solution. If there is, we may not find it. So we will be okay as long as we can beat the other methods, or we can be compatible with the other methods. That's what we are going to do. Okay. Any questions up to this point? So what are you guys reading at the back side, at the back rows? What are you reading? What do you have in your hand? You are reading something, right?
Yeah.
What are you reading? You are not supposed to read something else or watch videos, okay? If you are having difficulty reading this, come closer. See those people? You can use a chair. Okay, any questions? Yes.
Why do we use one at vector? I mean,
Where do we use it? Well, it's kind of it's just a representation. I didn't give examples of, I mean, where did I come to one hot vectors? I didn't give any examples of where we use the one-hot representation for vectors, but it's a vector representation and it is used. If you want me to give some examples, well, the only reason why we are using one-hot vectors is for some numerical methods. Some methods work very well for the one-hot vectors.
Encoder decoder maybe.
When you try to, well, that's one example, but it's not limited to that. For example, for the classifiers, it works very well. For example, what? Okay, it's your fault. You asked me, and I will have to explain it. Let's say I have a translation task. I read books, okay, and I give this sentence to a translation system, and I like this to be translated to Turkish, okay. So this translation system produces one-hot vectors every time I call it. It produces a vector of size, let's say 40,000, okay. In this vector, only the entry for the Turkish word ben, I, is high, like maybe 0.7. All the rest are close to 0, okay. So obviously this one is not producing a one-hot vector. It is trying to produce a one-hot vector, but it's saying that I am only 70% sure that the first word of this translation should be ban, okay. Then I will say, okay, you produce ban, I'm going to give you this, and produce me another word. It produces another vector, and it's going to be staplage, etc. And this one is going to be 0.8. In this kind of translation architectures, one-hot representation is very useful, okay. It is, well, you might say that why doesn't it produce directly vectors? I mean, what's happening inside these boxes, they are more comfortable with working with the one-hot vectors, okay. So I did not use any one-hot vector. I just told you that maybe this is one of the most stupid ways of representing a word with a vector. This is possible, but don't call it stupid because it is being used. More smart way of representing a vector is this, okay. 200 dimensional representation of word banking, and this is how you do it. We are going to come back to this one. So we have a very large equation and we are trying to optimize it, minimize it, so it turns into an optimization problem. And usually in the optimization world, you don't go for the most optimal or the optimal case, you go for the good enough case, and that good enough case will produce good enough vectors for us, okay. Good, okay, let's take 10 minutes of break. After the break I will continue and I will show you how to make that optimization. Hayret bir şey yani. Arkadaşlar bunu niye hatırlatmadınız bana ya? Söylediklerimin sesi çoğu buradan aldı sesi ve çok kötü çıktı. Neyse en azından kaydettim.
Nasıl o ses gelebilir? Restart attım onu bilgisayar hızını. O yüzden sonra bir baktım arkadan gidiyor. Disk yazar şeyi. Allah Allah. Bizi kazıkladın herhalde. Benim bildiğim yere oluyor işte. Bugün işte bir tane daha ekledim dedim. O yüzden bunu ekledim. Başka güne de alamadığım için kaldı. Gözükmüyor ki buradan. Şu şeyin yanında.
Okay, let's move on. So let's look at let's try to analyze this. Let's try to analyze this um, probability assignment to given that center word. What is the probability of the context word or the outside word thing? Okay, as I said before, this dot product can produce a scalar number between minus infinity to plus infinity, so we don't like it. With this exponentiation, we make it positive. And we do this for all the words possible between center word of all the words in my dictionary. Okay? So this is a very expensive summation actually, right? For Turkish Wikipedia, there are 1 million cases for that one. It's going to be very expensive. But we have to do it, or we have to do some kind of an approximation. This is for the normalization, otherwise it doesn't become a probability. Some people get surprised about this and they say that you don't get to define the probability for by yourself. Probability is something, okay, you will say that, okay, let me give you one example. Let me give you one example. Okay, I like to find how many male students, or the ratio of male students to female students in this department. And in the morning, I came to the beginning, the entrance of the building, and I counted 100 students, right? And out of 100, I see that 30 of them are female and 70 of them males. So usually with the maximum likelihood the estimation, you will say that the probability that a given person in this department has a chance of 30% being female. That's one calculation. But let's say I did this in the morning, I counted 10 people, all of them were females. Should I say it is 100% female, or I didn't observe any males? So this maximum likelihood estimation thing is not the only way to estimate the probabilities. It has some disadvantages, advantages, and etc. The probability for me is something different. I can calculate probabilities any way I like, as long as it is within the rules, as long as it produces some intuitive numbers between 0 and 1, it should be okay. This is how I measure my probability. And if this probability obeys all the rules, then I can use it. That's what I am doing now. Okay? That's what I am doing. And this probability is very nice. Okay? This probability is very nice. It assigns non-zero numbers for all the cases. Okay? Given the center word something, what is the probability of all the other outside words happening? It's going to assign something. It never says 0. It never says that these two words cannot come together. It always produces something. Doesn't matter if it's very small. It always produces something. So I like this kind of stuff that produces some results, whatever the words are. Usually this is called a softmax function, okay? And this softmax function can produce a probability for all the cases. Let's say out of this expression, the maximum one could be one of the classes of n classes. So I'm going to assign something to it, but addition of all these alternatives would add up to 1.0. And we use this function a lot in deep learning, and in this case, I am going to use that too. So let's go back a little bit and let's look at this. Let's look at this large. Can you imagine how large this one is? Okay. We are talking about vectors. Let's say our vectors are 200 dimensional. Okay. If our vectors are 200 dimensional, if I have 1 million words in my dictionary that I need to assign that I need to assign vectors, okay? And nobody asked it, but let me tell you, okay? We are going to assign different vectors for the center words and the outside words, okay? If banking is at the center, okay, we are going to call it, okay, UC. If it is outside, it is UO, okay? So I have two of them, that's why in these equations, where are my equations? Yeah, or it is not U, okay. It is V and C. V is for the context center words. U is for the outside word, the context words. Okay, two vectors for each word. So I am going to come back to this again. Two vectors for each word, 200 dimensional vectors, and there are 1 million vectors. So that means what? This many parameters that I need to find, this many numbers that I need to find for each vector, okay? For each vector there are 200 and I need to find 2 million of them. And that's a very large space to figure out. That's why it's a very complicated problem. So assigning random numbers from the beginning and making small modifications to those numbers will not work very well. We have to find something better, and we are going to use this gradient descent approach that works very well, okay? Suppose my function is as simple as this, okay? It has just two variables. I had 2 times 10 to the power 6 times 2 times 10 to the power 2, right? This is 200. So it is 4 times 10 to the power 8. What is 400? 400 million parameters in my case. This one has just 2 parameters, okay? I like to find x and y, right? I like to find the minimum of this equation. What kind of values of x and y, z becomes minimum? You might say, well, you might say that it is easy to see 0 and 0 will make it 0 because I see it, but you see it because it's a two-dimensional problem. Can you tell me the same thing with the 400 million dimensional problem? Of course, you would not. But usually, we develop our numerical methods and we test them on these kind of simple environments. And we test it. If it works, then we apply it to these kind of environments. That's what we are going to do. We are going to use this idea of gradient descent, but again, even this one is complicated. Let's make it, okay, this. I am trying to find the minimum of, okay, this function. Where is this a single dimensional problem? Where is this function, where does this function produce the minimum number? Of course, you're going to say, of course, it is 0, but let's try to find it numerically. What did I say? We are going to start from a random vector assignment, and we are going to move from random towards better solutions. That's what we are going to do. Let's say I started from this position. Let's say it is x is minus 2, okay? And if I put minus 2 in here, it's going to be 4. Do I know that minus 2 is the smallest value, that is the value that produces the smallest x square thing? Well, I don't know. How am I going to do that? This is the rule. You take the derivative of this x square. It's going to give you this slope, right? If I follow the slopes trend, slope is slope towards right, and I will say that, okay, if I go to right, I am going to the smaller parts of this function. That's what I am going to do. So let's take the derivative of it. Derivative is f, okay, f prime, but For our case, I am going to use this gradient operator, okay, is 2x, right? Okay, so I take this 2x. If I put in here, it's going to give me, okay, fx, okay, it's going to give me -4, right? X is -2, this is -4. -4 means the slope of this thing, okay, slope is going this way. So let's go to the inverse direction of the derivative. So -4 is a large number. I need to multiply it with something. So this is what I'm going to do. I will do this fx, okay, minus derivative of fx. That will lead me towards a smaller number. But this number is a very large one. Maybe I should multiply it with a constant like this. For example, 0.5 or 0.2. Okay? So if I multiply with this with 0.2, okay, what am I gonna do? It's going to be, oh, sorry, this is not fx, it is x. I am going to take this x and I'm going to move it in this direction. -2 -4 times 0.2 is going to be, let's say, I don't know what it is. I think it's going to be what? -0.8. Let's say it is -1, okay? If I choose this alpha in a correct way, it's -1. So it became -1. If I do it the same thing again, -1 minus, if I put -1 in here, it's going to be -2 again. So, and I have alpha here too. -2 times alpha is, what was alpha? 0.4? So it is going to be, it's going to be, because minus is going to be 2 times 0 point is going to be what? 2 times 0 point is going to be 0.4, right? It's going to be minus 0.6. So as you see, I came to 0.1, 0.6 is going to be this, and I will end up at here. Because at this point, my gradient will produce what? 0. At 0, this one will produce 0. I cannot move left or right. If I have started from the other part, okay, then this equation would have produced exactly the same thing, but it would push me towards this side. So if the slope is very large, I move fast. If the slope is small, I move slower. Okay, it's a numerical approach. It's found by somebody, I don't know, Newton Raphson, I don't know, a long time ago. Even before the computers, they used to solve problems like this. It's a very well-known numerical solution to these kind of problems. You said that you might say that I don't have to solve it numerically. I know the analytical solution to this x squared thing. Just take the derivative of it and equate to 0, and it's going to final, etc. Yeah, that's true, but I mean, these are very simple examples. If I give you this, okay, if my function is z is equal to 5 times x to the power 100 plus 7 times x to the power 98 plus etc., 100-term polynomial, you take the derivative of it, you will have terms like x to the 99, and good luck solving this kind of a solution, okay? Finding this kind of a solution. Numerical methods are better. So this is what we are going to do. We will take, okay, derivative of this function that we like to minimize, which is expressed, okay, which is expressed, why why do I keep losing this? Okay, which is expressed this way. This is already that one. Take the derivative of this function with respect to what? These parameters. Okay, 400 million parameters. And try to move it to a better place that produces smaller numbers. Then do it again and again and again until you say that I cannot move any place better than that. I have to stop at this point. Okay, so it's a very large thing. Taking derivative of all these numbers is not a very easy thing, but we have to do it. And the fact is that if you write your code smart, you can take the derivatives, and you can move your theta values to better places. And at the end, you will see that you are assigning very nice vectors for each of those words. You are going to assign two vectors. Okay, one vector for that word as a center, and the other one for the context. Okay, two vectors for each of them. And if you put them back, you will get your probabilities like that, logical probabilities, or for the logical vectors. There are a few things that you can make this optimization. Okay. By the way, if you don't believe this, just open an Excel and you can try it yourself. Okay, so let's say I have a function. I am going to write a function. Can I make this bigger? Can I make, how do I make, okay, let's make this bigger. Like this. Why it is not bigger anymore? What's going on? Do you guys know how to make this? Yeah, okay, I found it. Good. So I say, let's write the equation, okay? Let's go to this one and multiply it with itself, x squared plus, or let's make it more fun, x to the power 3, so that we wouldn't, okay, I'm going to change it later. X squared and then plus y squared. Okay, this one, and plus 19. Okay, let's put some numbers in here, 1 and 1. I like to make this, I like to minimize this. So what am I gonna do? Well, maybe I should make these absolute numbers so that...
Move it to C.
What?
Move this cell to C and copy down.
Yeah, that's what I'm going to do, yeah. That's what I'm going to do. A1 and that and that. I am putting those dollar signs in there. When I copy it, okay. Okay, so that's A and B. So what am I gonna do? What is the derivative of this thing? It is A. Oh, okay. I don't want to do this with A. Actually, let me do it with just one variable A. I don't want to introduce the second one. So it is A squared times, okay. So what I did was, if I can write it, do it again. So x cubed plus x squared plus 19. That's what I did. Okay. And how am I gonna update my values? Remember the formula? What was the formula? Formula is this. Formula is this. Take your old parameters and subtract this alpha times the derivative of your objective function. Okay, what is my derivative of the objective function? Okay, make this a little bit smaller. Can you still see it? Yeah, I think you can. So I am going to put the derivative in here. So what is my derivative? My derivative is going to be 2 times, well, 3 times, or why don't I copy this here and put it in here, right? And modify it. This is the derivative. So 3 times x squared plus 2 times x, and 19 goes away. And this is my derivative. And let's write this equation. And this one is going to give me, my new parameter is going to be equals this one minus, what is my alpha? Let's make this alpha, right? This times derivative is here, like this one, right? This one, I guess that's it, right? So make this 0.1, 0.1. Okay, so I think I shouldn't have done this with the dollars, right? Is that correct? Because I am going to put it, right? So if I take this like and copy it, it's not going to work. It will be always the same thing. Yeah. So what happened? Did I mess it up? Okay. So make this not dollar, A1, A1, A1. Right? Okay. And this one is good.
B may be fixed, B2 may be fixed, B1, sorry.
Okay. And this one is at the wrong place too, right? Oh, this maybe, what?
3a squared plus 2a.
Yeah, this is correct, but this is wrong because first I will put this in this position, right? This is going to be what? It's going to be A1 minus, yeah, it's dollar here, B1, B1, why? Oh, okay, B1 times what? Times the derivative of it, it is E5, it's correct, right? Okay, good. When I started from 1, it became 0.5, right? And this one is going to change a little bit. Yeah, like this one and get back. And I'm going to do the same thing here too. See what's going on? And it is getting smaller and smaller and smaller. I think it's going to be, I think just pull it down like that and do the same thing here and pull it like that. It's getting smaller and smaller. It's going towards like, it's getting towards like 0, right? 0 is the minimum of it. Okay. At the beginning, it just started from 1. I started from 1. Let's start this from 12. What happened? Oh, it got so, what?
you should enlarge itself.
Well, no, it says the number is too big. Ah, wow, that's because, you know what happened? No. It is a negative number, then negative number, then negative number. There is something wrong with this. Let's make this 0.01. Yeah. You know, did you see what happened? I made this alpha very big, so it took a very large step. That large step messed up everything. Because with the large step, I went way away from my solution, and I don't know how this function behaves in those areas. That's why it has to be small. Let's make even it is smaller. But if I make it smaller, it's going to converge very, very slowly. But it is converging. 0.1. If I start this from, let's say, 90, again, maybe I should make this even smaller now, right? For some reason, yeah, it is getting smaller. It's going towards 0, much stable, and move this like that. Okay, what happened? I couldn't get it right. It just, oh, okay, because I didn't do these. Yeah, it's getting smaller and smaller, but I guess this is too small. Now I know what you're thinking. If we are playing with this system, gradient descent system, for a single equation like x to the power 4 plus x to the power 2 plus 19, if we are playing with this this much, how are we going to solve this 400 million parameter problem? Well, I didn't say it is going to be easy, but this is the way to go. So if you solve your problem for a single case using this one, take the derivative, move towards the opposite side of the gradient, and calculate your value. Do it again, do it again, do it again, and you will find your minimum. This is just a single dimension. But if I like to do this for multiple dimensions, then I want to take maybe partial derivatives. Derivative of this function with respect to x is 2x, right? That's it. So 2x will give me how much I should move in the x dimension, and 4y will give me how much I should move in my y dimension. It is just two-dimensional. If it is 400 million dimensional, then it's going to give me 400 million dimensions. And if I multiply all those numbers with my alpha, okay, in that case, if I move along that line, I will find my optimal point, or at least locally optimal point, for that problem. And believe it or not, it works this way. And we start with such a large theta. In this theta, I have 2 times 200 times 10 to the 6 elements. Okay, very large vector, and each vector element is just a real number, and I need to find the optimal values for this vector, each of them. And using the gradient descent that I showed you, you run it for your data set, and it will find the result for you. The thing is this: it is very difficult to take 400 million dimensional derivatives. Okay, it is difficult, simply difficult. So how are we going to take it? We say that, okay, let's assume I have only this sentence, maybe 5 other sentences, okay? So that makes this problem like this. I have only 5 center words and 5 times 4, 20 outside words. Total of 25 words. At a step, I am going to update only the theta values of those 25 words. Okay? And I keep doing this until I scan the whole data set. And I do this again and again and again until I don't see any improvement. So lucky for me, I don't have to take 400 million dimensional derivatives. I only take 25 times 200, which makes 2000 dimensional. 2000 dimensional derivatives, which is much better than million dimensional derivatives. And that will make things workable on a real computer, because I don't have that kind of memory on my GPU or on my cache. So it has to be small, okay? That's called stochastic gradient descent, okay? That's called stochastic gradient descent. And with the stochastic gradient descent, people have shown that this system works, okay? So, so far I told you the skipgram model, okay? So remember, given the outside word, what is the probability? No, just the opposite. Given the center word, what is the probability of outside word? We can just do the opposite. Given the center word, what is the probability of the, given the context word, what is the probability of the center word? Is my continuous bag of words. Skipgram and continuous bag of words, their just probabilities are different. Instead of U as V banking, you just say U banking V as, okay? So you are changing this arrow directions. That's it. For some cases, for small data sets, I think skipgram works better. For larger ones, continuous bag of words works better. They are proposed by 2 different groups, and they work equally good, okay? And they are sold in similar ways, okay? So we talked about the gradient descent. This is the basic thing. The whole, you know what's happening with the world, right? Everybody is doing deep learning. Everybody is doing machine learning and the neural networks and etc. At the core of any deep learning algorithm, we have this, okay? We have this gradient descent. We optimize, we find our parameters using gradient descent optimization. This one, okay? You have lots of parameters in your model. You need to update those parameters so that your next iteration would produce better results for you, okay? So this is a standard algorithm that works under the hood with a few more bells and whistles, okay? Everything since 1960s, we keep doing the same thing, and for the last 10, maybe 13 years, where the deep learning people started showing very, very good results everywhere, this rule did not change, and people are not happy about this. Very old algorithm, very primitive algorithm, as you see, very inefficient too. But we don't have anything better than this to optimize, to find those results for the general case. For specific cases, maybe you may find some results, but for all cases, this is the way we solve things. And in a simple Excel sheet like that, if you play with this learning rate thing, and if you write your derivatives, okay, correctly, then you will find your solution. Okay, you will find your solution. That's it. Well, I mean, most people, I bet if I take the current literature and current results and take them to the top computer scientists of 25 years ago, none of them would have believed me that we are achieving these kind of results with this kind of old technology. Even the inventors of this these techniques, okay? So it's kind of surprising that this is happening. Yesterday or last week, something very critical has happened. They have found a faster matrix multiplication algorithm. DeepMind, did you read about it? Matrix multiplication. Read about it. Let me try to. Okay. Google News. They have a Nature, the journal Nature, right? Matrix multiplication. Okay. Discovering faster matrix multiplication. I think they are doing 30% faster. Let me see. Yeah. I think the last development in matrix multiplication was 50 years ago. Somebody crazy invented a method for multiplying 4 by 4 matrices with 7 multiplications instead of 8. So he is doing like maybe 15% faster, right? 7 instead of 8. Now they are saying that we found an algorithm to multiply matrices 30% faster, okay? This guy, the Strassen algorithm, you know how they teach you the matrix multiplication, right? You take the rows and you take the columns and you multiply. Basically, you do the dot product between rows and columns and you add them up, right? There is a trick. I think you are reusing some of the multiplication and etc. Nobody understand, okay, this Strassen guy's solution, but you see that it works. Yeah, I know. I mean, how you find it, okay, where did you come it? We don't know, but it works. Now using this alpha tensor stuff that they invented, they can do it with even more understandable ways of multiplying stuff. Now everything is 30% faster. What does that mean? It means that what we do in deep learning is just matrix multiplication, because I didn't tell you the whole story yet. We don't do a single level optimization. We have multi-level optimization, and each level is a matrix actually. We keep multiplying matrices because we have so many parameters and they are interacting with each other. So in a single night, everything got 30% faster, and at least 30% faster. In some cases where you do continuously many matrix multiplications, then the speed up will be even exponential maybe. So who invented this? Artificial intelligence level algorithm invented this. It says that these are the results, okay? I did reinforcement learning, and it works better than what you are doing. And these are the results, and we have to believe it because it works. It produces the same thing in a smaller amount of time. And even this algorithm uses this optimization method. Okay, so we are stuck with it until somebody finds a better solution to optimize these kind of problems. We will keep using this. Okay, gradient descent. Don't forget about it. Okay, and stochastic gradient descent, I already talked about it. The problem is, okay, you cannot handle the whole j theta. It is very big, okay? So what you do is, I take 5 word windows and take either 2 or 6 or 8 or 4 or 16 or powers of 2 windows, and only change the theta parameters of those words at each step. And don't use the same order of taking the windows. Change your order stochastically. Take the random ones. Take the random windows. Okay? That's why it is called stochastic gradient descent. And it is the best optimization algorithm that we use, that we know that works for the general case of optimizations for any neural network based deep learning stuff. Okay. I think I'm going to take a break. Does anybody have any questions? And I'm going to, yes.
Does this algorithm calculate the derivative of the function, or it takes 2 points of a line and calculates that?
Well, if you know the mathematical formula for your functions, of course, it is the derivative is automatic, right? And usually we know it, but sometimes we take the derivatives numerically too. Numerical derivative. I mean, it is easy for me to give you this x square and drawing this graph and taking the derivatives is good because this is a very well-behaving function. Sometimes I don't have it. Sometimes I have points like these. Okay? In this case, finding the optimum for a single dimensional case is easy, but 100,000 dimensional case is going to take some time. So we use both of them. But usually for these kind of libraries, you give your function, okay? It takes all the derivatives automatically, and it calculates the gradient itself, okay? But I didn't tell you the whole story. I think in the next lecture I am going to give you the more complicated part because we are not going. It is not going to be enough just as solving this x squared thing. It's going to be solve this and later solve this and later solve this kind of approach. Okay. So when we come back, I am going to show you the manual page of the Word2Vec. Manual. By the way, you can download Word2Vec. Where is it? Yeah, this is tutorial Word2Vec download. You just download it Word2Vec. How to download it? Yeah, code Word2Vec tool. Okay, it is inside Google. So you are going to see that it's a C code of 200, 400 lines of code. That's it. And it calculates all the stuff for you. But I am not going to show you the code, but I am going to show you the manual, how we use the...
It may be in GitLab, I think.
What?
GitLab.
It is in the, definitely is in GitHub, yes, that's true, but well, just a minute. Let me find options. Command line options. Do I have the, okay. Okay, see this is continuous bag of words. You give the outside words and try to estimate the center one. Skip gram just the center one and the outside words. Okay. Why don't I, okay, here are the options. Size. When you run the Word2Vec, okay, of course you give your data. That's one thing. What is your data? Your sentences, Turkish or English sentences. 1 trillion of them, okay? Size is the number of dimensions. How many dimensions you want for each of your vectors? 200, 400, 100, it's up to you, okay? It looks like they have chosen 50 as the default one, okay? Window is the maximum distance between the target word or center word and the context of it. Default window is 5. That means it's going to be 5 times 5 plus 5 plus 1, 11 words being looked at. Minimum count of words to consider, okay. It says that if a word kitaplarıymışçasına did not happen more than 3 times in your corpora, I am not going to calculate any vectors for it because I don't have much statistical information about that word. It's going to ignore it. Okay, this workers is, I think, now the number of partitions during training and the default worker is, I guess this is the number of threads that's working on the problem because this is highly parallelizable process. You can take your windows for different part of the corpora, and since you are updating the theta values for that region only, it is fine. And SG is the, do you want skip gram or continuous bag of words? And that's it. But I think there are many more, okay, this is good. You know the similarity between this thing. I think there are other options. For example, this is a very expensive calculation. This one is a very expensive. Which one? This one. From 1 to n. N is the number of words in your dictionary. So I don't want to calculate this all the time, but I have to calculate it. Why? Because I have to normalize it. It says that only calculate for a number of words. That's going to give you some idea. Okay? So don't use it. Maybe use it for the 100 words only, random 100 words only. That will give you an approximation. It's an approximation, but it works very well. So this means that instead of running this loop for 1 million words, I am going to run it for 100 words. That's going to be 10,000 times speed up. Okay? Of course, I am sacrificing some precision for that. There was an option for that too, but I couldn't find it. Okay? So why did I talk about this word-to-vector representation? This is what we are going to do. Remember, we like to compare two sentences. Okay? In our previous case, can I find it? File, where are my, can I find, maybe it is here, there? Yeah, 29 of them. Okay, edit distance. Remember what we said about using the edit distance for comparing two sentences? Yeah. What is the edit distance between these two sentences? Well, I expect that, I mean, these are exactly, they have the same exact vector, right? Their vectors are very, very similar. In fact, they are the same. How about this one? Okay. Confirms and said, kind of the same. They should have similar, they should have similar vectors. So substituting this one with this one should be less costly. Okay. I don't have another substitution in this case, but the cost of substituting this kind of stuff should be less costly than cost of substituting two unrelated stuff. So in your homework number 1 or 2, you're going to use this. You're going to calculate your word vectors, and to do these calculations, you're going to use your vector differences. Okay? And maybe some other bells and whistles that you're going to invent later. That's why I like to talk about this. Any questions so far? Okay, no questions? Well, in that case, let's take some break. After the break, at 16:40, we will continue with our word-to-vector discussion.
Az önce Word indirmeye mi çalıştınız bir tane?
İndirmeye çalışmadım, menüyü bulmaya çalıştım.
İndirmeye çalıştıysanız şeyde vardır diyecektim. Hugging Face.
Her tarafta var ya. Yani orada ver CD kodu varsa ben göstereyim diye düşündüm ama sonradan da vazgeçtim. Arkadaşlar yoklamayı imzalamayan var mı? Bir de yoklama nerede?
Sen isteyecek mi abi?
Okay, if our word to vec assignment of vectors works fine, but remember we are trying to assign 200 dimensional vectors. Somehow, let's say I converted them to two-dimensional vectors using some kind of a technique. That means what? I am ignoring 198 less important dimensions. In 200 dimensions, this is what I get, okay? Completely, okay, completely unsupervised. I did not mark anything. I just give unprocessed text. See this year, month, summer, okay, Samsung, Nokia is close together. This is Wednesday. How about this? Yeah, Venus, Mars, Pluto is on top of each other, as you see. What else? Yeah, library, educators, publications, science, studies. As you see, the meaning-wise, if they are close to each other, they found very close places in this two-dimensional world. And it behaves much better in 200-dimensional world. But since we cannot visualize it as human beings, we can see at most like with our eyes, 3 dimensions. More than that, we have to use our brain. Brain means mathematics, but usually this helps 1 or 2 dimensional representations. So this is what we are trying to achieve, and it just can be achieved in a very simple way. And the nicest thing about this is it is all learned without any human markings. Remember the WordNet? WordNet requires a few PhDs to mark all those words and everything, which one is similar and etc. This one doesn't require that. Okay. So we achieved that representation using the principle of tell me your friends, I'm going to tell you who you are principle, or a word, you shall know, or you shall know a word by the company it keeps principle. But there are other ways of finding these vectors. Okay, it's called co-occurrence matrices. Okay, co-occurrence matrices. This co-occurrence matrix calculation is very simple actually. Okay, let's say in my Wikipedia dump I have only 3 sentences. I like deep learning, I like NLP, I enjoy flying. Okay, and I like to give in these 3 simple sentences, I like to assign vectors to these. And very simple. Of course, don't expect anything useful out of it, just to demonstrate it using this co-occurrence matrix. Okay, this is what I do. I happens with like 2 times. I is seen with enjoy 1 times. And that's it. So that means that our window has a width of just 1. So I am just looking at the neighbor, left or right neighbor word. So I happened 3 times, and these are the neighbors. 2 times like, 1 times enjoy. Like happened, okay, 1, 2. It has 4 neighbors, 2 eyes, 1 deep, 1 NLP. Yeah. Okay. And you know the idea, right? So is this symmetric? This is symmetric, right? Say symmetric or not.
Yes.
Okay, so let's ignore this part then. We can look at the upper part. Okay, so I already have, let's not ignore this part, okay. I already have vectors, right? This is a vector. This is a vector, right? So enjoy has a vector like this. There is a 1 here and 1 there, right? So that means what? If I have 1 million words in my, 1 million unique words in my corpora, if you make such a matrix of 1 million by 1 million, okay, well, most of those values will be zeros because there are many words, like 99% of the words would not come together with other 99% of the words, right? So that table will be only 1% occupied. 1 million by 1 million is a very large number, right? It is 10 to the 12. What is this? Trillion? Is it trillion? Yeah. It's a trillion-sized table, very large table. We don't have that kind of memory on our computers. So representing such a matrix for very large corpora is not that easy. That's why these co-occurring matrices are not very scalable. They work well for small data sets. For large data sets, word-to-vec approach is a better approach. Okay, so let's continue with this one. Okay, with the co-occurrence vectors. Okay, you increase the size with increase in size with vocabulary is problematic, very high dimensional, requires a lot of storage. Okay, and the sparsity issue is a problem because I mean most of them will be zeros. Are they really zeros or they did not occur in my case and etc. So for some cases, I don't know. I mean, like and flying did not happen together, but that's because my corpora is not large enough. So maybe I shouldn't trust these kind of zeros. Zeros are not really zeros. Remember with the word-to-vec approach, no probability of P given OW is 0, right? It has some kind of a value. So this behaves much better. That's what we are saying, okay? So sparsity issues is not good. So models are less robust, but they make better use of small amount of data like this one. Even with this approach, let's see that one, okay? Even with this approach, we are going to see some very nice results, okay? Very nice results. As you see, this one has, each one has 8-dimensional, 1, 2, 3, 4, 5, 6, 7, 8, yeah. See, dot is a word. Dot is a word, okay? That's a very important word because it shows you the end of the sentence, and end of the sentence has lots of meaning. So each word has an 8-dimensional vector. Again, how am I going to show 8-dimensional vector on a piece of paper? I need 2 dimensions. For that, we usually use principal component analysis. And the principal component analysis, you should know this from your linear algebra course. Okay? It says that given a matrix, square matrix or rectangular matrix, doesn't matter, you can always factorize this matrix into 3 parts. For any matrix, okay? One is a diagonal matrix in the middle. Diagonal means that all the non-diagonal elements are all zeros. And if there are non-zero elements in this matrix, they are in the diagonal. Okay? So this is a diagonal matrix like this. Okay? If there are zeros in the diagonal, those zeros should be at the lower right. Okay? It could be all zeros. If they are all zeros, okay, then the whole matrix is a 0. But if there is a single non-zero entry, it should be this one. If there are 2, then it should be these 2, etc. That's the sigma part. Okay. This U and V are special. They are within themselves. They are all orthogonal to each self. So if you dot product these 2, you will get a 0. If you dot product these 2, you will get a 0. Okay. So why are we talking about this? We are talking about this because I can represent each of my my vectors, this is the original matrix. Okay, this is my original matrix. Okay, instead of using this original matrix, I can use for example, let's say in this diagonal, let's say I have only two non-zero elements. Okay, that means that rest of them can be ignored. If it is ignored, then these two numbers are only important, or these two numbers are only important. Just ignore the rest of them. Okay, so I can use just this two-dimensional vector instead of this three-dimensional vector, or in the case of that one, instead of this five-dimensional vector. Of course, I am losing some data, but you are keeping most of your data with this approach. So it's called data reduction approach, dimensionality reduction approach. It doesn't reduce any data. Actually, data is the same data. It's an approximation. You say that I have this much data. If I am okay with losing 5% of the information within it, can I use just two dimensions instead of 5 dimensions? Or can I use, let me go to the first slide. Instead of 200 dimensions, I like to use just 2 dimensions. I know that I am going to lose some data, that's okay. Give me just 2 dimensions, and it gives you 2 dimensions, and I can show you in 2 dimensions that way. So I am applying the same thing to this data, okay? Instead of representing each word by 8-dimensional vectors, I am going to represent each one by 2-dimensional vectors. And in a Python code, okay, NP, I have these words: I, like, enjoy, etc., etc., etc. Remember, this is the matrix symmetric, same matrix. I am using singular value decomposition, okay, and it gives me 3 matrices. This is the S matrix in the middle, that is the diagonal. So I can use either this one or this one to get the first 2 important dimensions. That's what I am doing. See, it is using U matrix and the first element and the second element of the U matrix for all of them. So it says that for the like word, get its position, 2-dimensional position, from the U matrix, from the 0th and the first element of the columns of each. Okay? It says that like is a word by itself somewhere. Okay? Enjoy, learning, flying, they are coming together. Deep and NLP is here, and I is separated. It kind of makes sense. I mean, very, very small amount of data. They are grouping together related stuff. Okay? With this kind of small data, word2vec is not going to do anything. All the results will be all random. For the word2vec, you need tens of thousands of sentences at least. Okay? But for this co-occurrence matrix, small data works. Okay, small data works, but it doesn't generalize. That was the problem with the artificial intelligence techniques. The techniques that were developed in 1960s, 70s, 80s, 90s, 2000s they work very nice for the toy problems, but they didn't scale up. With the deep learning, they work very well for the large-scale data. In fact, they work much better than the small-scale data, and we are going to see some examples of it. Okay, so this is the co-occurrence matrices. With the co-occurrence matrices, there are lots of problems. For example, the, he, has, in the happens a lot, right? Thousands of times. Okay, so we have to do something about it. Some people say that don't count them if it is larger than 100. Or sometimes they say that, why are we talking about this and his and has? I mean, these are all occurring everywhere. I am going to ignore them. Some of them ignores them, okay? So lots of solutions for those. Okay, and these are from 2005 paper. These are some of the examples of two-dimensional projections of 100-dimensional data, whatever. Okay, as you see, all different forms of take, they are very, very similar. All different forms of show, they are at a very similar position and speak and etc. So similar functioning stuff are coming together nicely. Okay, and they realize that I can use this kind of a space to write our classification systems. How many people know about SVM? Okay, how many people heard about it? You don't have to know, just one more people. SVM is a classifier. Let's say I like to write a classifier for a word. Given the word, it says that this is a noun or verb. Okay, it's a system as function as it will take a word. It will say either it's a verb or noun. Fiil ya da isim diyecek. Okay. So how am I going to write such a classifier? You could say that I can take all the words in my dictionary. Okay, I can take all the words on my dictionary, and at the corresponding definition of the dictionary, each word is marked by either verb or noun. That's my classification system. Or you could do this. Get the co-occurrence matrix of all the verbs and nouns and project them in this two-dimensional space, and try to find a line that divides this space into two like that. Okay, how do you define a line? Line is defined by two parameters, m and b, right? Y equal to mx plus b. Okay, that's how you define a line, right? So find me a line by finding this m and b, okay, that separates this word into two. At the upper side of this line, okay, there will be names. At the lower side, there will be verbs, okay?
Can we use k-means algorithm?
K-means is used as an unsupervised method to cluster the stuff. I mean, your suggestion is let's use, the question is this, can we use the K-means algorithm to cluster these words into two groups? But you would not know that if it is be clustered this cluster one and this is the second cluster, because they may not cluster the way that you want, okay? Because it's a fully unsupervised method. You are saying that give me two clusters. Maybe it's going to cluster it maybe in a better way. This is one cluster, and this is the second cluster. Okay, we don't know how it's going to behave because we are not telling K-means anything about a word being a noun or a verb. Okay, so what I am saying here is that, I take in this space, I take 100 verbs and nouns. I mark them as 100 verb and nouns, and I ask the SVM to come up with such a line. Once it finds the line, any new word that I put into my system, I will find its two-dimensional representation. If it is here, it's a verb. If it is here, it's a noun. Right? That's as simple as this. The better thing is, I don't have to project the 200-dimensional vectors into 2 dimensions. I can work in 200 dimensions because SVM can work with the hyperplanes, okay? It doesn't have to work with just 2-dimensional world. It can work with 200-dimensional world. It works, okay? It works much better with high-dimensional spaces, okay? So people have been working on this kind of stuff. Again, it worked nicely for 1 million word corpora, but it didn't work for 1 trillion word corpora. That's why we are kind of away from these kind of approaches. But still, we like these. We say that these kind of co-occurrence matrices are very good with small amount of data because it uses the statistical relationship between words like this very well. Maybe we shouldn't forget about them. Okay, maybe we shouldn't forget about them. So these newer approaches, there's a continuous bag of words or skip grams. They scale very well with the large corpus sizes. They don't use the statistics very efficiently. They need lots of data. Okay, and they are very generalizable. I train it on this kind of Wikipedia. Okay, let's say I trained it on Wikipedia and I'm running my system on the scientific papers. It works very well. And it can capture complex patterns beyond word similarity. Okay, and we are going to see what this means. The other one is, okay, it is very fast. But training is just simply forming the matrices, right? That's it. And it uses the efficient use of statistics, but again, it doesn't generalize very well. It doesn't generalize very well. Somebody came up with this idea of, okay, GLOW. Combine the ideas from both of these worlds, okay? Word frequencies, co-occurrence matrices, along with the word-to-vec ideas. It's called GLOW, okay? Remember 2013 is the word-to-vec, 2014 is the GLOW. It works better than word-to-vec, and they applied it to many problems, and they see that it works very well, GLOW approach. And some of the results for GLOW, okay? You say that, okay, I am going to give you lots of sentences about biology and etc. Okay, find me the similar words to frog. Okay, as a human being, and well, English my not native language, but I know frogs is similar to frog, toad is similar to frog, but I don't know this one. I don't know this one. It can say that, okay, these are very similar. These are the 9 most similar words to frog.
I think they are species name.
Yeah, well, sure. They are not synonyms, but yes. Anybody knows what? Okay, I like this one, but I don't know its name. This is the best one. This is the common frog. I don't know what it is. Okay, so the many ways of, okay, let me give you some other new ways of representing the words. Birth is something that we use all the time. It's new, okay. It is based on deep learning and encoder-decoder stuff. Before birth, there was fast text. Fast text is very good for Turkish because fast text says that I am not going to assign vectors to the words only. I'm going to assign word parts. When I say, okay, masamdaki, okay, it says that I am going to assign a vector. I am going to assign a vector to this word masam, then this word, then this word, then this word, okay? So it kind of overlapping subwords, and I am going to assign vectors to that. And the vector for the whole word is the multiplication, okay, pointwise multiplication of those vectors, or not the multiplication. It is the addition of all those vectors will make up the vector for this whole masamdaki word. So this is good for Turkish. Why? Because we have many forms of the same word in Turkish, And I like the vector for masa and masamdaki to be very similar, right? Word2Vec already does that, but it needs to see lots of masam and masamdaki in the similar context. FastText doesn't do that. Okay, FastText doesn't do that. FastText does not need to see. Even FastText has this nice property. You see. Okay. Üçer beşer. Somebody wrote this word like üçer beşer as a single word. Maybe true, maybe right. FastText can assign a vector to it without saying this word even before, because say that I have seen this before, I have seen this before, I will add them up. That will make the vector for this üçer beşer. And it works very nice. So it's much better for Turkish than Word2Vec, but the idea is the same. Word is even better. It does the same thing, but it says that, okay, it says that this word, when I see it, okay, it should have a different vector depending on the context. Masalı okudum, the vector for masalı okudum, the vector for masalı in the sentence masalı okudum is very different from masalı oda. Okay, they are two different things. So I'm going to assign two different vectors to these words. Okay, so it pays more attention to the context that is happening around the word. Okay, so that's one of the big problems with the FastText or Glow or Word2Vec kind of approaches. They take the words by themselves without paying any attention to the context. Context is very important. Okay, if the context, okay, masalı oda, masalı sandalye, prenses masalı, etc. They are all very different, and masalı oda and masalı sandalye, even if these two are used in different contexts, they should have different vectors. That's what but their vectors should be more similar than story-based masala. Okay, so don't forget about these. I think I will talk about them later when we dive into deep learning world later. Okay, this is important. We keep assigning vectors to the words, but we don't know if we did right, if we did correct or not, right? Okay, we don't know if we did right or wrong. So how am I going to evaluate it? There are two ways of evaluation, and this is usually the case for all types of NLP applications. You find something, you say that it works nice, and they tell you, show me. Okay, how are you going to show me? The easy way is the intrinsic one. You come up with some kind of a test. Okay, I'm testing it this way. The second type of test is this. I am going to use your invention in a real NLP approach, NLP problem. For example, machine translation. For example, summarization. If the final results are good, then your method is good. So let's talk about this intrinsic evaluation first. It is easy, it is fast to compute, but it is easy to play with, okay? It can fail from time to time, but this one is an extrinsic one, is robust, because I used to use Word2Vec in my machine translation system. Nowadays I am using Word, and my machine translation results are much better, okay? So this is a much stronger proof that your method works, okay? But let's take this first one, intrinsic one. People play these kind of games, okay? This is called analogy. If man and woman are related, using the same relationship, what would you say the corresponding part would be for the king? The answer should be queen, okay? And this is the calculation how you should do it, okay? A and B are the words, of course they are vectors. This is what you do. Subtract the vector of A from vector of B and add C to it. Okay, now you get a new vector and scan all of your vocabulary to find an xi that makes this multiplication largest. Okay, it's kind of this. Find this vector, the black vector between man and woman, okay, and take this vector, let me do this, and take this vector, put this vector on top of king, and among all the words around here, choose one that is the closest to that position. It turns out that it is queen. This really works, okay? With Word2Vec or FastText or the Glow, it really works, okay? And it's called analogy. It's called the analogy test, okay? You are finding the analogies. And again, this is all discovered unsupervised way. You scan the Wikipedia, you train your vectors, you extract your vectors, and you ask this question. I'm going to give you Ankara and Turkey. Now I'm going to ask you Athens. And it gives you the answer Greece. Okay? So you say it knows geography, right? I mean, this one knows about the human relationships. This one knows about the geography and etc. I think I have yeah. This all works. Okay. You say that find the vector between man and woman, this vector, okay, and well, I am not showing it in 200 dimensions, just two dimensions, and if I take this and put it on brother, the closest word at the end of this vector is sister. If I take it and if I put it in where Duke, right here, the closest word comes back as duchesse. Duchesse, duchesse. How do you read? Duchesse, duchesse, whatever. I don't know. Okay, it works. And if I put it under on top of uncle, aunt comes the closest one. It's like magic, but it works. Okay. So the first time a professor of age 60 who spent his 40 years of academic life on NLP, when they see this kind of result, and like maybe 10 years ago, 15 years ago, they went crazy. Okay, how come there was this guy Norvik, okay, important guy Norvik. He has a paper, not paper, formal paper, but maybe white paper, unreasonable efficiency or effectiveness of data. Train your system with more data, it captures these kind of relationships. Read about that. When did he write it? Norvik, unreasonable effectiveness of the data. Yeah, well, is that a real paper? Yeah, well, he wrote it with some other people. Unreasonable effectiveness of data, and it appeared where 2009. Yeah, around those times people realized that, and this is crazy. I mean, if you find the correct algorithm, if your algorithm can efficiently deal with your data, more data means that I am going, especially the first page is very to the point. Say, I mean, human beings are trying to find this kind of stuff. F is equal to ma in 1600 years, okay? 400 years ago or 100 years ago, they try to find these kind of compact equations, compact formal ways of explaining my observations, okay? And we try to do the same thing for English language. And somebody said that can I make this larger? Like, okay, I hear this. The grammar for English language is now 1700 pages, and it's still not complete. It doesn't work, okay? If you try to formalize English language, this is the result, and it still doesn't work. I mean, I cannot come up with such a nice compact formula for English language. What are we going to do? And during those days, they realized that more data, better statistical algorithms, and data is more efficient. Nowadays, they are talking about let's ignore these kind of rules, even for physics. It is all about machine learning. So your observation, all of your observations, if I observe this in the real world, tell me what should I observe out of the movement of this object. That's what's going to be happening. So read this one. That guy says that, okay, this is unreasonable. I don't understand what's going on, but it works. In 2010s, by the way, this guy, this is one of the brains of Google, in the early times of Google. He gave them the directions. I think he's responsible for the NASA's deep space exploration. They are using artificial intelligence techniques, and he's the author of the artificial intelligence book that is used all over the world. So when he says something, you listen. So that happens. So we don't understand what's going on, but it works. Of course, I mean, we have a very easy way of explaining stuff once the stuff it's like after the soccer game, football game happened, it is very easy to talk about it and explain why we have lost or why we have won, but nobody talks about it before the game happens, right? So after this thing happens, we have lots of explanations, but still we don't know what's going on with the data. But data is the key with all areas of the artificial intelligence. So why don't we make this course about data? I don't want to do it that way because I like to teach you how we have been doing this stuff and what the new stuff too, so that you can see where we come from. Sometimes, for example, the edit distance. Nobody uses edit distance much, but it is a very nice algorithm, and in other places maybe you can use the similar kind of algorithm. And I'm going to do the same thing for all the cases that we are going to cover. Okay, by the way, yeah, do you know what this is? I think this is from 2015s. These are the companies, and these are their CEOs, okay? So if I know this vector, I add this vector to this Vodafone, and I find his CEO. Without telling anything about what CEO is, without telling the system anything explicitly about what a company is, but it works, okay? And this one works too. If I add this vector to any adjective, it becomes, okay, slow becomes slower. And if I add this vector to this green one, to any of these adjectives, it becomes the superlatives, okay, slowest. It knows about the grammar, it learned about the grammar, okay? It learned about the grammar. So these are all intrinsic stuff. So somebody talked about it, analogy evaluation. So they ask these analogies, they ask these kind of questions to many people, and their mean performance, they ask the same questions to SVD kind of approach, that is a singular value decomposition approach, and we are talking about GLOW, remember GLOW, uses both of words. Skipgrams, continuous bag of words. It looks like these are semantic analogies, syntactic analogies, and this is the total. It looks like GLOW is doing the best. Okay. This is a very old data, okay? Nowadays they are doing much better than 300 is the number of dimensions that you assign to the vectors. Okay, and more data helps. Wikipedia is better than news text. That's what happens. I'm not going to talk about it much, but I am way out of my time, but I need to stop here. Let me stop here and we will finish this up next week. Okay, any questions? Good. Okay, I'll see you next week.